This tutorial we are gonna learn how, based on a real value UEL, I'm here with another PhD student, and here is gonna learn how to complexify such UEL. So with ZFEM, that is a complex variable finite element method, we are gonna be able to compute layer derivatives with respect to the perturbed variable. So we are gonna work with a very simple example, which is a cantilever beam with an applied load at the end. And for the purpose of this tutorial, we are gonna work with a one element mesh. Okay, so the first thing that I'm gonna do is here in my terminal, I'm gonna go and log in into Shamu. So Shamu is the super, give me 1 second. So I'm just gonna go here and log in into Shamu, which is the supercomputer that we have here in UTSA. And with my username, which is AZC408. Sorry. I'm gonna type my password. And then we are in Shamu, okay? I'm gonna load module SGE, and then I'm gonna log in into a particular compute node in which the members of this lab has access. That is minwater.q. Okay, so I'm now in compute node 005. Okay, here in this screen, I am able to go directly to Shamu and work on the files locally in my computer. So I'm just gonna go here, and I'm gonna go to this folder that is called ZFEM tutorial. And today we are gonna complexify an UEL, which is only first order UEL. Okay. So I have two folders. One is real, then which is we are first gonna work on the real value UEL, and then compute the node and displacements from the example that I'm gonna show, and then we are gonna complexify and compute some derivatives. Okay. So the first thing that we are gonna do is that this is the example that we are gonna work today. So we are gonna use an 8-noded quadrilateral element. So that means that it has 8 nodes, 9 integration points, and in the local, or like in the natural space, which is epsilon and z, it looks like this. Okay, sorry, eta and z. So this is the example. So it's gonna be a one element example. So it has a length of 4 meters and a height of 1 meter, and we are gonna apply a displacement at the right end that has a magnitude of 0.01 meters. The elastic modulus is gonna be 200 gigapascals, and the Poisson's ratio is gonna be 0.3. Because we want to go simple at first, so it's easier to track the bugs or different errors that we might have. We even might have some errors today, because we are gonna create it from scratch. We are gonna work using a one element mesh. So it looks like this. So we are gonna manually work on creating this mesh, and then we can compute the displacements for this particular example. So the first thing that I'm gonna do is I'm gonna go here, and I'm gonna start working on this input file. It's gonna be Abaqus input file that is called 1LM real. Okay. So I'm just gonna make this screen smaller so I can have the representation of the mesh. Okay. So the first thing that we do is we type heading, and then this is like the name that we want to assign to our analysis. So it's gonna be one element mesh, and it's gonna be the tutorial for real value UEL. Okay. Then it's gonna be using an user element. So it's gonna be user element. Type is gonna be U1, that means that it's user defined. Because we are using a real mesh, we are using 8 nodes, so we type here nodes equal to 8. It's gonna be a 2D example, so the coordinates is equal to 2. That means that we only have 2 active coordinates. Bar here is how many variables I want to store when I'm working in my UEL. So depending on the number of state-dependent variables, this is for each element. So this is an user-defined element. That's the number of variables that you might want to store. So just start with 10. We might not even need 10 for this particular example, but I just want to go big in case I need something. And properties, here, actually this one is like a fake value, because when you define the properties, if you have more properties than the one you define here, that number is going to be overridden, okay? So this is just like a dummy number that while you define your coordinates. Then in the next line is going to be the active degrees of freedom of your element. 1 means displacement in x, and 2 means the displacement in y, okay? Then we are going to start defining the nodes. So I'm just going to type here node. So node number 1 is going to be in the coordinate. If we go here, is this here. I'm just going to put the axis in here, in the center of the beam, in the left side, okay? So my node number 1 is going to be in x equal to 0, and in y is going to be negative 0.5. Okay, my node number 2, which is going to be the right lower edge, is going to be in x equal 4.0 and y negative 0.5. If I do an error, just let me know. Node 3 is going to be 4.0, 0.5. Okay, then my node here, I had an error, is 3, then my node number 4 is going to be x equals 0.0 and 0.5. And then we go to the inner nodes, like in the half element length. So the node number 5 is going to be in x equal 2.0 and negative 0.5. Node number 6, which is this one, corresponding to the center, like in the center in the y axis, but in the right edge, it's gonna be 4.0, 0.0. Node number 7 is gonna be in 2.0, 0.5. And the last node is gonna be 0.0, okay? Now we have defined our nodes, okay? Here I like to define a node set, so that this is the way that you define a node set in Abaqus. Abaqus actually doesn't matter if it's lower caps or upper caps. I just like to work in upper caps, and it's gonna be nset equals, and this is your node set name. So I'm just gonna call this one all nodes, okay? And because I don't want to type 1, 2, 3, 4, 5, 6, 7, 8, I'm just gonna give an Abaqus command that is called generate, and it's gonna generate with intervals of 1 from 1 to 8, and this is the interval number. So it's from node 1 to 8 with intervals of 1. That's the node set that is called all nodes. Then let's go ahead and define the elements. So I'm just gonna type here element. The type is gonna be U1, and here I'm just gonna define the L set name, right? and I'm gonna call this one all elements. And how many elements we are gonna have? One. So the first value is the element ID, and then here you have the connectivity. So it's gonna be 1, 2, 3, 4, 5, 6, 7, and 8. Actually, is with this numbering, because we are working with the Abaqus numbering, that is like this. So we define our nodes like that, and the connectivity is actually like that. Okay. Then we are gonna define the node sets, where we are gonna define some boundary conditions, right? So we have to define a boundary condition in the left edge and another one in the right edge. So let's define a node set, and then node set name is gonna be left edge, right? And what are the nodes that are in that one? So it's gonna be 1, 4, and 8. So it's gonna be 1, 4, and 8. Correct. Then I'm just gonna copy this one so I can define my right edge. So it's gonna be the right edge, and the nodes are gonna be 2, 3, and 6. So it's gonna be 2, 3, and 6. Okay. Then I'm just gonna, this is for the output frequency, that's standard, you don't have to mess with that one. And then here, in the Abaqus input file, a comment is with double asterisk. So let's define a comment so we can start defining here the material properties. Okay, so the way you do it is asterisk, which is calling like an intrinsic Abaqus function, and it's gonna be UEL UL property, and that property is gonna be assigned to the L set, to the elemental set. How do we call that one? All elements. So I'm just gonna copy that name. That means that you can have multiple sections defined by elements, so you can assign different material properties. Okay. So the way I have defined the UEL, so let's go and check the UEL, is that my elastic modulus is going to be the material property number 3. The Poisson's ratio is going to be the material property number 4. And then I have other properties that I use in order to define either boundary conditions or perturbations or things like that. So in the UL property 1 and 2, I use those for like when I have thermal conductivity and the thermal expansion coefficient. So I'm just gonna give like dummy values in there, because the first two I don't care about those. And then I'm gonna give the number 3, which is the elastic modulus. So it's gonna be 200 gigapascals. That means that everything that I have from stresses or anything is gonna be in megapascals, right? Because to the 10 to the power of 3 megapascals is a gigapascal.
Yeah, but is our problem in meters or in meters?
In meters.
So we need to put that.
Yeah, no, I'm gonna write that.
As long as you are consistent with the properties, it's gonna be fine.
Okay.
Luckily, Antonio's made me rewrite some of his papers.
And then the Poisson's ratio is gonna be 0.3. Okay. And those are the only 4 variables that I need, right? Let's check here in my UEL where else I have these props. So I'm just gonna look here. So I only work with the props 3 and 4. So those are the only 2 properties that I care about. Okay. And then I'm just gonna define my step. So it's how the Abaqus is gonna solve on one type of boundary conditions I'm just gonna have. So it's gonna be on a step. I'm just gonna assign it a name. So it's just gonna be pull. okay, and it's gonna be an static analysis. This first one is like the smaller increment size. This is like there are 4 different values. So this one is the initial increment size. This one is like the minimum increment size. This one is the end of the analysis. So we are gonna load until 1. And because this one is linear elastic, I just gave that my initial increment size is gonna be 1.0 because it's not gonna have any convergence issues. Okay, then after my step is defined, I'm just gonna define the boundaries. So boundary. Okay, so where am I gonna define a boundary? So in the left edge, so I'm just gonna go here and like, is in my left edge, I'm just gonna say that my x displacement is gonna have a value of 0. Why do I have 2 ones? The first one is like how many boundary conditions you're gonna define, and here is the value or like the direction of that boundary condition. Sorry. Or no, it's like the initial degree of freedom that you are gonna restrict, and this one is the final degree of freedom that you're gonna restrict. Then in the same left edge, my initial boundary condition that I'm gonna restrict is gonna be the number 2, and I'm gonna restrict also the movement of that one. So this one is totally fixed. It's not the best way, but that's how we are gonna work with that. Instead of having these 2, what you can do is left edge, and you're gonna say that from 1 to 2 is gonna be 0.0. So that's the same thing, but I just like to do it like this. So those are the boundary conditions here for the fixed part of the beam, and then I'm just gonna say right edge, and I'm only gonna apply a load in the one direction, which is dx. Okay, and the displacement that I'm giving it here is 0.01. So 0.01. Okay. Then I'm not defining loads. I'm doing my analysis and displacement control. So that means that I can finish my step. So I'm just gonna say end step. Okay. Then we can go again here, and I'm gonna go to that folder which is located on the ZFEM tutorial. So it's gonna be ZFEM tutorial. Then I'm just gonna go to first order, and I'm just gonna load the modules that I need in order to run. So I'm just gonna load Abaqus. The version is 6.12, and the compiler is Intel 1364-bit. Okay, I just realized that I need an environment file, because this format of this UEL is a new format. So I just need an environment file to tell the compiler that I'm working with that kind of file. So let me grab that file, which is this one, the Abaqus VC, that tells the compiler that we are working with new format. This bash script is something that I use so I don't have to type everything. So the way that I call an Abaqus job is Abaqus job input file and everything. So here I just do it from the script. So I just call this script and it runs the analysis for me. So in order to verify, so in this part in here, I'm just gonna have some node print. So I'm just gonna say node print, and the set where we are gonna print is gonna be all nodes, and let's print the displacement in x and y. With that, we are gonna be able to verify our UEL. Okay. So I'm in the folder, and I'm gonna call the script that is called run.sh. So I'm just gonna go to real, and actually I have to load a module in that folder, and I'm just gonna type run sh and my analysis should run. Let's see if we don't have any errors in the creation of the input file. There we go, we have some errors, so let's check here in the DAT file. I have a plus in somewhere in here, so that was my error. I'm just gonna run again, and we're gonna say overwrite the files.
And although we're a little more accurate because they are getting 4.2
Another error.
higher.
Let's go to the DAT file again.
So let's use this one mesh as part 1. What's that?
Here is not nodes, is node. Sorry about that. Okay, so the analysis is completed, and then we go to the DAT file. I'm just gonna wait a little bit so it updates because it's communicating with the cluster, and it's showing the displacement for all the nodes. So let's bring our example here. We can tell that it's not plotting or it's not showing the results for nodes 1, 4, and 8. Why? Because the displacements are 0. So if it's 0, it doesn't show it in there, unless it has a value in there. Okay, so we can see that where we apply the boundary conditions, which is 2, 3, and 6, so 2, 3, and 6, the displacement in y is, in x is 0.01, and then the intermediate nodes is somehow very close to 0.5. Okay, so that's the UEL. I'm not gonna go over the specifics of the UEL, just later when we compare the real value and the complex value UEL. But basically in an UEL, what you have to give Abaqus is your right hand side and your stiffness matrix, which in the case of a A-noded quad is gonna be 16 by 16 because you have X and Y displacement. Okay. So now with that, let's go and create the complex input file. Okay. So I'm just gonna go to the folder that is called complex, and I'm just gonna name this one element complex, and I'm gonna delete everything I had in there. Okay, so we can start from scratch. This first part is somehow very similar, so the heading and everything, but here is the tutorial for complex valued UEL. So the thing is that because we are now using complex coordinates, right? Instead of having one node, we are gonna have 8 nodes. We are gonna have 16 nodes, right? Because we are gonna use real and complex parts. So we are gonna use a complexified element. So actually, let me bring a presentation that shows that. So this is how it looks, right? So previously we had this element. Now instead of having only 8 nodes, we are gonna have 16 nodes because we are gonna duplicate the coordinates. Okay, so now here, instead of having 8 nodes, we are gonna have 16 nodes per element. And it's still, the degrees of freedom that are active are still 1 and 2. Okay, so I'm just gonna go here and define the nodes. So node. So the real nodes are gonna be exactly the same as the ones from the real value UEL. So I just copied those from the real value UEL. Then we are gonna define the complex nodes, right? So for that, I could start at 9, but it is easier for me. Actually, let's start at 9. Okay, so node number 9. Okay, but the coordinates of that one are gonna be 0.0, 0.0. They don't actually have coordinates because the only reason why they exist is because they carry the derivative information. So later in the UEL, all the derivative information is gonna be stored on those complex nodal coordinates. In the case of a shape perturbation analysis, if you do a material perturbation analysis, the nodal coordinates are not gonna be complexified, but the stiffness matrix in the complex part is gonna be complexified. So I'm just gonna go from 9, 10, 11, 12, 13, 14, 15, and 16. So I'm just gonna manually change those nodes. So now node 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so I just defined my nodal coordinates. So let's define two different node sets. So base like in this one, I'm just gonna copy that line. So I'm just gonna say I'm just gonna create my real nodes. So let's call those real nodes. So it's from 1 to 8, and I'm gonna define my complex. So complex nodes that go from 9 to 16 with intervals of 1. Okay, now let's go to the element definition. I'm just gonna copy that from here as well. So from element, I'm just gonna say
125.
all elements, because the elements are not duplicated. The only thing that is duplicated is the nodal coordinates, but the element, what is duplicated is the amount of nodes that it has. But the number of elements from a real to a complex valued mesh is actually the same. And here I have to type 9, 10, 11, 12, 13, 14, 15, 16. Okay. It is very important that after here, that is where when you start the complex coordinates, if you look at this image, you can see that the node number 1 and number 9 are connected. So here, the first node of the real has to be connected with the first node of the complex plane. Okay. So we just define our elements, and then we are still gonna define the boundary conditions. So I'm just gonna copy those two, which is left edge and right edge. The thing with the boundary conditions is that you have to define it for the real and for the complex nodes. So those are gonna be called real, and I'm gonna copy those and create some ones that are from the imaginary. So my node number 1 in the real, in the imaginary, corresponds to the node number 9. That's correct, right? So I'm just gonna, instead of here being 1, I'm just gonna type 9. So that's a little bit, I don't know, for me it's a little bit complicated, right? So I showed how to do it, but now I'm gonna change the way I do it. So here I like to do something like 1001, and then 1002, and so forth. So like 1000, and here I'm just gonna copy those values from 1 to 8. I'm just gonna paste them in here. So now my complex coordinates go from 1001 to 1008. So it's easier for me to see which ones are connected and which ones are not. So I have to change the complex nodes. So they go from 1001 to 1008 with intervals of 1. The connectivity also changed. So it's 1001, 1002, 1003. Actually, this one is 10,000. 004, 1005, 1006, 1007, 1008. Okay, now it's easier for me to see that the left edge, the imaginary coordinates are 1001, 1004, and 1008. And the left is gonna be, sorry, the right is 1002, 1003, and 1006. Okay, everything clear so far?
Yes, sir.
Okay. From the real value UEL, I'm just gonna steal this part. Okay, which is the definition of the frequency for the output and the step definition. Here the properties, let's check our complex UEL. So if I go here to props, find props, it changed, right? So my property number 1 is the elastic modulus, and my property number 2 is the Poisson's ratio. So instead of having those initial 2 dummy arguments, I'm just gonna delete them. Okay. And I'm also gonna assign it. So, okay, let's do something first. So I define my UEL properties, and I'm gonna define an initial condition and it's gonna be a temperature boundary condition. So why am I doing this? Because we don't actually have temperature in this one, but I wanna say, hey, the nodes number, let's go to here. The nodes number 3, C, X, and 2 are gonna be perturbed. So for example, I can perturb those nodes in this direction, in the horizontal, positive horizontal direction, to see what happens if I have a longer beam, right? So if I take those nodes and I apply a nodal perturbation over there, I'm just saying that those nodes are gonna be longer, right? So it's like, hey, what happens if my beam is longer? So I'm just gonna say that in my node number 2,
I don't think it will change much.
in the node number 6, and in the node number 3, I'm just gonna have a dummy temperature that is gonna be 1.0. There's another way to do this that is called with predefined fields. So with field number 1 or field number 2, but for now I'm just gonna work here with temperature. I can show you how to do it with fields later. The step doesn't change, the step definition doesn't change, and we have to define the boundary conditions. So I'm just gonna borrow the boundary conditions that I defined in the previous one, in the real value UEL, and I'm gonna say that my left edge, I changed the name, right? So they are now gonna have to be real. Okay, so the same thing that I did for the other one, so my real boundary conditions. And if I apply a boundary condition in the real one, in the imaginary coordinates, I have to also apply the boundary condition but with a value of 0, right? That's in order for the system of equations to solve, right? Because if one is defined in the real, it also has to be defined in the complex. So I'm just gonna borrow these ones, and then I'm just gonna say that it's gonna be imag. Imag, right? And instead of having a value of 0.01 in the right edge, it's gonna have a value of 0.0. So you can check that all the sorry.
We'll get a higher value because of that.
So all the like nodes where I define a boundary condition in the real, I also have to define it in the imaginary, but with a value of 0. Okay. Then we go to the output. So we are also gonna print in here. So let's print for the real nodes the U1 and U2, and for the imaginary nodes or the complex nodes, also let's print the X and Y displacement. I don't wanna do any kind of perturbation, so these nodes right now are gonna be 0. I'm not applying any perturbation, so we can actually comment this part. Okay, and then I go to end step, and with that we have the complex input. Let's talk a little bit about the differences between the complex and the real valued UEL. Okay, so here I have on the left the real valued UEL, and on the right I have the complex valued UEL. So you can check here that all my variables on the real valued UEL are real, right? The difference is in here that the variables that if I apply a perturbation to the, for example, the elastic modulus, my Hooke's matrix, like my material matrix, is going to be complexified, right? Because that material depends on the elastic modulus, right? So here the complex variables are those that if I apply either a material perturbation or a load perturbation or a shape sensitivity perturbation, are going to be complexified, okay? So not all variables in a complex UEL have to be complex. Only those that if you apply a perturbation, then they're gonna be modified, or they are gonna carry the derivative information. Okay. So for example, let's check here the definition. I don't know why. Okay, the definition of the elastic modulus, right? Which is a very important parameter. In here, we just say, hey, the elastic modulus is the property number 3. You remember that it was the property number 3. In here is a complex variable, right? And the real part is the property number 1, which is the normal elastic modulus. And here in the imaginary part is gonna be 0, right? Because I'm not perturbing that input variable. If I wanna perturb it, here I just apply perturbation, let's say 1 to the negative 10. Okay, but right now we are not going to apply any kind of perturbations. Okay, here I also have a variable that I call HZ. So that's the perturbation that I apply to the imaginary coordinates, right? And for example, let's check how I create the material matrix. You can check that in here, in both in left and right, they are created exactly the same thing, right? So in order to complexify this part, you didn't have to do anything, right? Because we are using the intrinsic complex that Fortran has, so it can take care of all the imaginary algebra operations. So actually nothing changes, right? In this part, you can check that nothing changes. The only thing is that now my elastic matrix, it has both real and imaginary parts. So my entry, I don't know, row number 5, column number 5. In this UEL, it's a real value. In this UEL, it's a complex value, so it means that it has a real and a complex part. So I have to decompose my complex stiffness matrix into something that is called the Cauchy-Riemann representation of a matrix. Okay, so the Cauchy-Riemann representation of a matrix looks like this. So in the first, in this quadrant is going to be the real part. So in the diagonals, you're going to have the real part of the matrix or the variable. In the upper right hand side is going to be the negative imaginary direction, and here is going to be the imaginary direction. That is because Abaqus doesn't have a complex solver. So if, for example, you are using Python and you have your own code, you just say, hey, I have this value, this stiffness matrix, which is complex, go ahead and solve it. But Abaqus, it doesn't have a complex solver, okay? So what you have to do is give it a matrix that is entirely real value. So you just take a complex variable and you decompose it into this representation just so you can have all real values. So in here, where I'm giving Abaqus my stiffness matrix, that is the keyword that Abaqus has for the stiffness matrix, a matrix. Look that from, like, what's the size of my stiffness matrix for this element in the real stiffness matrix. So I have 8 nodes, correct, and 2 degrees of freedom per node. So that means that is 16 by 16. Now in complex, how many nodes you have? 16. And how many degrees of freedom you have per node? So 2, right? So the real x and y displacement and the imaginary x and y displacements. Okay. So here you can check that from 1 to 16 and 1 to 16, which corresponds to this part, is gonna be the real part of my stiffness matrix. So let's work with that in here. So you can check here that from 1 to 16 is the real part of the stiffness matrix. Also for this part, which is from 17 to 32. So it's from 17 to 32 is also the real part. Now in the upper right corner, so if this is 32 by 32, that matrix, that means that is gonna be from the rows 1 to 16, and then the column 17 from 32. So that is that part that has the negative imaginary direction. Sorry, the negative complex coordinates or complex values of my complex stiffness matrix. Okay?
Yes, sir.
Now the same thing goes for the right hand side. So the right hand side that Abaqus is solving from 1 to 16 is the real values, and from 17 to 32 is the complex values. Okay. And here in particular, in the S-bars number 1, I'm storing the strain energy. And in the S-bars number 2, I'm storing the the derivative of my strain energy. Okay, so that's more or less a little bit a fast explanation. I'm gonna just give you the UEL files, but you can see that in terms of the algebra and the operations that we are doing here, nothing changed, right? The only thing that changes is that you are using now the type that is complex. Okay. So I'm just gonna go here again, open my terminal, and I'm gonna go to the complex. So the input file is one element CMX. That's correct. The UEL file that we are gonna be using is 2D elastic complex. That's correct. So I think we can run and check if we get the same answer. Okay. In the derivative, you remember that we have an output for the complex nodes because we are not perturbing any variable. That should be 0. If it comes with a value, it's because we are applying a perturbation somewhere. Okay. So I'm just gonna change my directory and go to the complex, or actually how's, yeah. So it's gonna, we are gonna go to the complex, okay? So I'm just gonna go ahead and run my script, which is basically the same thing that I used here previously. You can see that it takes a little bit longer, right? Because it's solving a matrix that is twice its size. It has an error. So let's go ahead and check the DAT file and let's check the errors that it has. Okay, I have an error in the names.
It's an
underscore here, right? Okay, let's run it again. It's good that I have errors, right? Because then you can see how to find the error.
But make it incremental like last time.
Now it's running, so that means that the input file was correct. Let's see if the UEL is correct.
Yeah.
It says illegal memory reference. Let's check. Maybe it's because I'm giving or reading the property number 8. Let me check. So it's complex in here. Actually, I think it's because this part. I'm not doing a shape perturbation, and this is for shape perturbation. So I'm trying to read a predefined field, right? Because that, which is that dummy temperature, but actually I have it commented in here. So it's trying to read something that doesn't exist. Hopefully that's the error. Copy. Yeah, that was the error. Okay. Now, time to check the answer. So now you can see that I have the x and y displacement for the real nodes, and in the complex nodes, all values in this table are 0. Okay, let's compare those. So you can see that these values and these values are exactly the same. So that means that our UEL is correct. Now let's apply a perturbation. Okay, so the way to do it, hard-coded, like, right, because you can do everything from the input file using like flags. So like you have a property here that it's, I don't know, 1. So let's do it actually. Let's modify that complex UEL. So let's do 2 types of perturbation. So if is the property number 3, right? So if property number 3 is equal to 1, so then you apply a perturbation to the elastic modulus, right? So here you put HC, which is the magnitude of the perturbation. And then your Poisson's ratio is not complexified. Okay, you can either do that one, just saying that in your imaginary direction you have a value of 0 that I defined here in the beginning of the analysis as 0.0 double precision 0, or you just can say like, hey, it's only the property number 2. That means that it only has a real part. Then you say else if props number 3 it's equal to 2, correct? Then it's more or less the same thing, right? But the elastic modulus is only gonna be real, and your Poisson's ratio is gonna be complexified, and the imaginary part is gonna be HC. And if, okay, I like all caps, so like that. So you can like manage how you do the perturbations from the input file. Now that we have this so-called flag. So now we are gonna have perturbations with respect to the elastic modulus, right? So I'm just gonna leave this one in here, and I'm gonna run my UEL again.
Okay, that's fine, that's fine.
Okay. One thing that I forgot is that here in the step definition, you can see that the matrix that we are trying to solve, sorry, let's see where I have that file. This one is not symmetric. So you have to tell Abaqus that, hey, my unsymmetric solver flag is yes, right? So your unsymmetric is yes. There's actually a trick for that, right? So you can either say, hey, your unsymmetric solver is, the matrix that we are trying to solve is unsymmetric, or what we can do is trick Abaqus. And instead of, when I have my Cauchy-Riemann representation here, you remember that in the upper right hand side is negative. We can do it positive. And here now, in the input file, we say no, it's not unsymmetric. So that is actually super fast. I think it's 30% faster when you use a symmetric solver. Okay, so let's run again. Now that we modify the symmetry of the Cauchy-Riemann matrix,
So the way Unicode works is just forward slash.
okay,
Then you put in
and let's check the DAT file.
So if you're more familiar with Greek letters,
Just give me 1 second. It should be updating soon.
What is the difference in solving with the minus and without the minus?
yeah, you can do
Nothing.
the picking thing if you want to, but
Like if you put the minus, you have to use a symmetric solver. If you don't, you have to it's a symmetric solver.
So,
Okay.
but in the results there are the sign is changed or something. No?
No, nothing.
So why to use that representation instead of using the symmetric matrix?
No, it's because the Cauchy-Riemann is when you are doing Cauchy-Riemann algebra. But actually, we are not using Cauchy-Riemann algebra because we are using the complex, intrinsic complex, so it takes care of how two matrices are multiplied. Two complex matrices are multiplied. If you didn't have a complex, intrinsic complex in Fortran, you will have to do all the operations using this Cauchy-Riemann algebra. So we are actually only using the Cauchy-Riemann representation only so you can solve the system of the equations. So it actually doesn't matter if it's symmetric or unsymmetric.
I can go the extra mile and say, okay, this is what it actually is.
So
But this is
all
what
values
it
in
is.
this table are 0. So
Just to make it hard.
let's check if it's complexifying it or not. So here, I'm just gonna have a print statement that says elastic modulus has been perturbed. And I'm just gonna copy the same thing for Poisson's has been perturbed. So let's run again just to see if it's entering here, which it should. So now we are gonna see if it prints something in here. Let me see something. Maybe the step size is too small and Abaqus doesn't see it. Okay, let's check here. See nothing. So let's do a shape perturbation. Okay. And let's put here a 3 and let's activate those. So now that means that the nodes 2, 3, and 6, I'm just gonna move them to the right, but in the imaginary direction. So here I'm just gonna say 1 because that's the magnitude of the perturbation, and here in my UEL I'm just gonna activate this. So that's, I have this variable here that is called quartz aux. So that means that in the nodes where I define that fake temperature, I'm just gonna perturb them and then move them to the right. And I'm gonna move it in X. So the direction vector is gonna be 1 in X and 0 in Y because it's everything in X. And the property number, so that's only like if my property, let's copy this so we can know that we are doing a shape perturbation analysis. So if property is equals to 3, you say that nodal coordinates have been perturbed. Okay, and here is end if. So let's run that one. So actually you see here that in the input file is 1, but you know that the perturbation that we apply is super small. So here those auxiliary coordinates are perturbed here by HC, which is my perturbation step size. So I'm creating some complex coordinates. So that's one change that I have to do in the complex UEL. That is, instead of having real coordinates, you are going to have complex coordinates, which in the real part are going to be the real nodes, and in the imaginary part are going to be the complex nodes. So let's check the DAT file. Now we have some sensitivities, right? So you see that in the node 5 and in the node 7, that's the derivative of the displacement in X of the node number 5 with respect to like a longer beam. Okay, so if this is 4, right, so what's the derivative of the displacement of this node with respect to the length of the beam? So that's the derivative that we are trying to analyze. If you were to do like a verification of this derivative using finite difference, how would you do it? You take these 3 nodes and you just perturb them a little bit, right? So you make the beam a little bit longer. Instead of being 4, it's gonna be 4.001 or something like that. We are doing the same. We are perturbing those nodes, right? But we are perturbing it in the imaginary direction. Okay. So actually, yeah, you have one derivative over there.
What if we need that degree of freedom? We cannot use the temperature because it's a degree of freedom that we need.
Okay, so give me 1 second and let's do it like that. That's a very good question. So I'm just gonna have to pull something from here. So it's gonna be from, just looking for the file. One second. Okay, so you do this. So remember the value of the perturbations is 1. Sorry, and here this one you have to divide it by the perturbation step size, which was 1 to the negative 12. So
that's only delta coordinate of that, no?
Yeah, this is the derivative of the displacement in x with respect to a longer beam. So the derivative of this node
length of the beam.
with respect to the length of the beam. Because if we expand this part, it's because we are making the beam longer. So, because we are using temperature, we are gonna do this, right? So now we are gonna say it's gonna be a field. So it's gonna be field, and the variable is gonna be number 1. That's the only thing that you have to do one.
Okay,
So
it's good. You change the temperature for a field variable.
For a field variable, that is the field number 1. And actually in here, in my UEL, when I'm reading the perturbation, I'm reading it from the predefined field number 1. So nothing has to change. If you have several fields, if you're doing different shape perturbations, for example, if it's your field number 2, I think you have to change this one to the field variable that you have.
Yeah.
Okay, so that's a very good question. So let's go ahead and run it again with this change that we just did. And the derivative should be 1.25 to the negative 15. So let's overwrite it.
Yeah, we're used to doing everything first.
Errors. Let's see what the error is. So let's wait for this to update. The error, the keyword is misplaced.
That's about right.
Maybe after this step.
Yeah, it's after the step.
After the step.
No, I think here's fine. Field variable 1. Let's check if this. Yeah, let's run it.
Damn, that is more accurate. With a square?
I think it's running. Yeah.
Those numbers are like that.
Let's check the derivatives, and we got the same value. So that's how you have to do it because you are using temperature. So that's how you define the field.
Supposed to be more accurate.
Yes, sir.
Any other questions?
What other question do I have?
Really does. I mean, keep the data and stuff.
Not in this moment.
One thing to notice here, like in the
Yeah.
UEL properties, when you define an element, you can have 17 different values, which in the first one is this one, like the element ID, and then the 16 nodes. If you had an element that has more than 16 nodes, you have to use another line, right? Because when you are defining elements, Abaqus only reads 16 numbers after the element ID. And in here, when you are defining UEL properties, you can only define 8 properties per line. So that's something to have in mind. I don't know what else, but I think That should be it. Okay,
Very good.
thank you.
Thank you.